Hello, everyone. Thanks for tuning in. My name is Stefan Winkler. I'm Associate Professor with the School of Computing, and I'm also Deputy Director with AI Singapore. Today, I'd like to talk about analyzing human emotions, which has been the main focus of my research in the past few years. The motivation for this is really that a lot of the current AI work focuses on the IQ part of intelligence without considering the emotional component, what people call EQ. If you look at existing agents, they are limited in that respect. They will be able to answer factual questions and make scripted jokes, but not much more beyond that. So for next generation agents, we really look for them to better understand human emotional behavior, be able to react appropriately, whatever that means, and in the process provide a more natural interaction with these agents. So my focus today in this presentation will be the recognition part, emotion recognition, and specifically facial expression analysis. When we communicate with others, only a small part of the emotions is conveyed by what we say, by the words we use. Emotions are largely conveyed by nonverbal cues such as voice and body language. And of course, the face and facial expressions can highlight emotions and do particularly well because face is one of our most expressive body parts. Now, if you look at traditional approaches, they typically classify emotions into one of a small number of categories, typically 6 or 7, and you can see them listed at the bottom here. So you would decide whether a face looks sad or happy or neutral, and so on. Now, this approach has a number of limitations and problems. It works well when emotions are very expressive and faces are very expressive, as you can see on the top left here, but it doesn't work so well when the expressions are rather subtle, meaning close to neutral. And this is what I would argue is what you encounter mostly in real life. It also doesn't work well in certain situations where emotions can't be categorized well into a single category. You can look at the example of the two babies here at the bottom left. You can see that one face is positively surprised towards happy, and the other one is negatively surprised towards fear. Now, to us, this is a very clear distinction, and it's also an important distinction to make. But for a classification algorithm, they would put both of these faces into the same category of surprise. And finally, there are variations in intensity, which is also important to capture, as shown on the bottom right here. So in summary, it's difficult to differentiate the wide range of complex emotions using just simple categories because a single label does not reflect all the complexity that we can express with our faces. Now, the approach we've chosen is based on the emotion continuum. It follows what is called a circumplex model that was introduced by Russell. And you can see it shown on the left here. It's basically a dimensional representation of the emotion space. And the two dimensions in this space are valence and arousal. Valence tells you how negative or positive an emotion is. On the left half of the circle shows negative emotions. The right half shows positive emotions. Arousal tells you how active or passive an expression is. So at the bottom, you have the more passive emotions and expressions. At the top, you have the more active and energetic expressions. And you can see how Russell associated different words with different points in this arousal valence space. Now, what we have done is use this for mapping facial expressions onto this arousal valence space. So we've come up with a method to do that, which I'll talk about in a second. You can see different faces showing different expressions, different emotions being mapped onto this dimensional arousal valence space. What you can also see is that this arousal valence space not only captures arousal and balance, but also the intensity quite naturally. Intensity is essentially the difference or the distance from neutral, which is in the center of this space. So using such a dimensional representation of emotion, the problem becomes one of regression rather than classification, and it gives us a lot more flexibility and granularity when analyzing these expressions. We've developed different methods to do so, both based on traditional machine learning, like the PLS method that is shown on top here, as well as deep learning, like the multitask convolutional neural network that is shown at the bottom. In both cases, we essentially perform face detection and emotion detection concurrently and produce these emotion attributes, arousal, valence, intensity, as the output of the system. So these are estimated after analyzing the facial features and facial expressions. Now let me show you why a dimensional measurement is much more powerful than a categorical measurement. Here you have 4 different faces or facial expressions. On the left, what is shown with the bars is essentially a traditional classification method. You can see the 7 different emotions at the bottom of the gray bar: anger, disgust, fear, happy, neutral, sadness, surprise. You can also see that all these 4 images are classified as 100% neutral, meaning the algorithm doesn't detect any emotional difference between those faces and classifies them all the same. Now you can argue whether these faces should be classified as neutral or not, but they certainly shouldn't be classified in the same way because these faces do show different expressions. Now, if you look at our measurements, which is shown in the circumplex model on the right, valence arousal space, the red dot essentially represents the output of our approach. You can see that the red dot is not only away from neutral for all these faces, indicating that the method doesn't think this is a neutral expression, but it is also in different places for each of these faces. So the method is actually able to distinguish these expressions as different. So it's much more capable at picking up those small differences in expressions. Now let me show you some examples of how this works on videos. So we've developed this into a rather lightweight method where you can see a video being shown on the left. We detect the face and then some feature points in this face, particularly around the regions of the face that are the most expressive, including the eyes and the mouth regions. And then we do this mapping from the facial features to the emotion space, valence, arousal space on the right. And you can see the red dot that captures the instantaneous expression label or position in that space at any given point in time. So this is an example for just a single face. So only the main actor's face is being analyzed here. But you can also do that for multiple faces. And I'll show you another example here. Now, as you notice in this particular example, the dots in the emotion space are jumping all over the place, meaning the measurements have become much more noisy. And this is for 2 reasons. One is that the faces are much smaller than in the previous video, and also the faces are not shown in a frontal view. So they're often side views, which makes it much harder to already detect, not to mention analyze the expressions on these faces. But what you can also notice is the red dot, which actually shows the average over all the blue dots, over all the faces detected. So it tells you the average mood of the people in this place, which can be used to analyze the mood in a certain environment. And I'll show you an example of that later on as well. Now, I'd like to go quickly through 2 use cases. One is comparing individuals, like shown here. This was actually done during the previous presidential debate in the US, where we analyzed both Trump and Clinton in the same debate. And you can see that when we draw the heat map of all the expressions that we analyze for both of them, they look very different. So what it shows for Trump is that the expressions are mostly negative on the left half of the emotion space, negative valence. He hardly smiles, hardly laughs, rarely engages with the audience in a positive manner. Whereas for Clinton, you can see that her main expression is mostly neutral, as indicated by the orange space in the middle of the in the center of the plot. And she also smiles a lot more and laughs a lot more. As you can see, the heat map extending all the way to the right of the horizontal axis, the valence axis. So very clearly shows the differences between these two candidates in this case. And you could imagine using this, for example, for evaluating interview videos when you want to screen candidates and score them based on their reactions and emotional behavior. This is just one example. Another example where we applied to large crowds is we deployed our system in an MRT station for a period of time and captured all the faces we were able to detect. And then again, we plotted a heat map of all the expressions and emotions we could analyze. And as expected, the emotions in this space are in the negative region. So MRT station is not a happy place. People are rushing to work, rushing home. They don't want to spend time there. But now you can imagine using this as a baseline for improving such a space. So you can tell whether by reducing the crowds, by improving the flow of people, by improving train frequency, maybe this will have an impact on the emotional state of passengers and essentially customer satisfaction. So this tool gives us an objective measurement of crowd mood and customer satisfaction by extension. You can use it, of course, in public spaces, but also for other places like shops, restaurants, at events, conferences, and so on. So to conclude, there's really many applications of this system. Emotion AI is, of course, the overall term for this. We've talked mostly about facial expressions, but you can also combine this with speech and text analysis, gesture recognition, other types of analytics to build more comprehensive solutions. And this is also what we're doing with my startup, where we're commercializing some of this technology for these applications. And with that, I've come to the end of my presentation. I'd like to thank you for listening, and also like to thank the team of people, of course, that worked with me on developing the technology. If you'd like to find out more, please visit my website or the company website, and also feel free to drop me an email. Thanks very much.